In case of hypothesis testing, for comparison of two populations, there are four situations. First is when the populations are normally distributed with known variances. With unknown variances, there are three situations. The first one is where the variances are assumed to be equal. Second is where the variances are assumed to be unequal. And the third one is the dependent sample, a paired t-test. While sampling from a normally distributed populations whose variances are known, a z-test is used for the hypothesis H0, mu1 equal to mu2 at level of significance alpha, and the test statistic will now be x1 bar minus x2 bar upon square root of sigma 1 square upon n1 plus sigma 2 square upon n2, and the decision criterion follows exactly in the similar manner. Only thing is the alternative will be mu1 not equal to mu2, mu1 greater than mu2 or mu1 less than mu2, and the value to be compared is either absolute value of z calculated with z alpha by 2 or z calculated with z alpha by 2 and z calculated with minus z alpha. Consider the example of the above situation where researchers want to know if there is a sufficient evidence to indicate difference in the mean serum uric acid levels between normal individuals and individuals with Down syndrome. Now, the data consists of readings of a sample of size 12 of individuals with Down syndrome and size 15 of normal individuals, and for the two populations the means obtained are 4.5 and 3.4 respectively, and their variances are known to be 1 and 1.5 respectively. Let us define mu1 as the mean serum uric acid level of normal individuals and mu2 as the mean serum uric acid level of individuals with Down syndrome. The hypothesis to be tested is H0 mu1 equal to mu2 against H1 mu1 not equal to mu2 at the level of significance 5%. The data that we know is the sample size of individuals which are normal is 15, their mean is 3.4 and variance is 1.5, and for individuals with Down syndrome the values are 12, 4.5 and 1. If we substitute the values in the test statistic, the value of z is minus 2.569. The decision criterion will be reject H0 if the absolute value is greater than 1.96. Since 2.56 is greater than 1.96, we reject H0 at 5% level of significance for the given sample. Hence, the conclusion will be there is an evidence to indicate a difference between mean serum uric acid levels of normal individuals and individuals with Down syndrome. While sampling from normally distributed populations where variances are not known, but they are assumed to be unequal, for testing H0 mu equal to mu naught at level of significance alpha, a t-test is used where the test statistic is similar x1 bar minus x2 bar upon square root of s1 square upon n1 plus s2 square upon n2, but it is to be compared with t having v degrees of freedom, where v is calculated as s1 square upon n1 plus s2 square upon n2 whole square divided by s1 square upon n1 whole square upon n1 plus 1 plus s2 square n2 upon whole square upon n2 plus 1 minus 2. So, the entire test remains same except for the degrees of freedom which need to be calculated using this formula. The example is there is a travel agency surveying 15 customers in all who regularly take their families either on skiing or golfing vacations. The amounts spent by these families is listed in the table below. There are 9 observations on golfers and 6 observations on skiers. It is assumed that the variances are different, that is unequal. Can it be inferred that golfers and skiers differ in their vacation expenses? Let us define mu1 as the mean amount spent by the golfers and mu2 as the mean amount spent by skiers. So, now the hypothesis to be tested, H0 is mu1 equal to mu2 against H1 mu1 not equal to mu2 at level of significance 5%. The data given is N1 9, N2 6. When calculated, the mean of the first set of data turns out to be 3372 and for the second set of data turns out to be 4095.83. Similarly, the variances of the samples are as listed here. Now, if we apply the test statistic T, the value that we obtain is minus 1.5973. And if we substitute in the formula of V, the value turns out to be approximately 19. And the decision criterion for a not equal to sign in alternative hypothesis will be reject H0 if the absolute calculated value is greater than the table value. Since 1.59 is not greater than 2.093, we do not reject H0 at 5% level of significance. Hence, golfers and skiers do not differ in their vacation expenses. The third situation is where sampling is done from a normally distributed populations with unknown but equal variances. Again, a t-test is used for testing mu1 equal to mu2 at level of significance alpha, and now we used a pooled variance assuming that the variances are equal, a single quantity where the pooled variance is calculated by the following formula. Now, the hypothesis to be tested will have a decision criterion, reject H0 for H1 not equal to sign if the calculated value is greater than T with N1 plus N2 minus 2 degrees of freedom. So, once we calculate the pooled variance, since the number of observations, independent observations is N1 plus N2 minus 2, the degrees of freedom will now change to N1 plus N2 minus 2 in either of the decision criterion that is used depending upon the sign of the alternative hypothesis. The example in order to study this test is a men's softball league played either with a yellow ball or a white ball. It is assumed that a yellow baseball is easier to view in the night games. So, a sample of 10 games were tested on each of yellow and white balls, and the number of errors caused was recorded as given in the table. Assuming that the errors have same variances, the test to be conducted is for whether the number of errors reduced while using yellow ball compared to that of white ball. So, let mu1 be the mean number of errors due to yellow ball and mu2 be the mean number of errors due to white ball. So, the hypothesis to be tested is H0 mu1 equal to mu2 against H1 mu1, that is number of errors due to yellow ball are less than mu2, the number of errors due to white ball at 5% level of significance. The sample sizes are same in each case, that is 10 and 10. The sample means for the given data calculated and the sample variations calculated are as follows. So, with the given data, if we calculate the test statistic, the pooled variance turns out to be 2.4152 and when substituted in the test statistic gives the value minus 3.1654. Since H0 is mu1 equal to mu2 against H1 mu1 less than mu2, the decision criterion will be reject H naught if the calculated value is less than minus t at n1 plus n2 minus 2 degrees of freedom, that is 18 degrees of freedom, and hence the standard tabulated values of t gives us the value 1.734, which has to be attached with a negative sign. Now, since minus 3.1 is less than minus 1.7, we reject H naught at 5% level of significance for the given samples, and hence we conclude that the errors with the yellow ball are fewer than that of the white ball. We now have paired samples or dependent samples. This is a situation where we have two samples taken on the same set of units before and after a particular treatment, and again the hypothesis to be tested will be mu1 equal to mu2. The test statistic now will change to T is d bar upon SD upon root n, where di is calculated for every sample observation as xi minus yi, the observation at the ith position for each of xi and yi, where d bar is summation di upon n, the mean, and SD square is the variance of this difference xi minus yi, but with denominator n minus 1, since a degree of freedom is lost in estimating the mean used d bar. Since the test has dependent sample, this type of variance and mean is used. The decision criterion for H1 mu naught equal to mu2 will now have n minus 1 degrees of freedom, for mu1 greater than mu2 t 1 minus alpha n minus 1 degrees of freedom, and for mu1 less than mu2 t minus t 1 minus alpha n minus 1 degree of freedom. Since the sample is dependent, that is observations xi and yi are taken on the same set of individuals in two different situations, the number of independent observations is only n minus 1, hence the degrees of freedom will be n minus 1. The example to follow this test is a weight loss program, and the weights of women was measured before the weight loss program and after implementing the weight loss program, and the desired result would be anticipating reduction in the weight of women. So, let mu1 be the mean weights of women before the treatment and mu2 be the mean weights of women after the treatment. The same set of women is being recorded for weight before and after the treatment. Since the weight is expected to be lost after the treatment, H1 will be mu1 greater than mu2. We have a sample of size 9 here. If we take the difference between xi and yi, the value of d bar is 22.59 and the standard deviation is root 28.3. So, the value of t calculated turns out to be 7355. The decision criterion will be reject H naught if the calculated value is greater than t with n minus 1, that is 8 degrees of freedom, and the table value turns out to be 1.86. Hence, the decision will be reject H naught as 7.3 is greater than 1.8 at 5% level of significance for given sample. Hence, the conclusion will be the weight loss program is effective in causing weight reduction in those 9 women.